Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision.
Tonight it's my pleasure to welcome Corbin Covault, Professor and Co-Chair of the Department of Physics at Case Western Reserve University, and this is obviously presented in collaboration with the CWRU's Emeriti Academy. To quote Professor Covault, "Ever since humans began turning their eyes to the heavens, the question has persisted, is there intelligent life out there? Since dozens of Earth-like planets have since been identified, are we getting close to answering that question?" Please welcome Professor Covault.
My name's Corbin Covault. Again, I'm here in Cleveland at Case Western in the Department of Physics. And I'm going to talk to you about the search for extraterrestrial intelligence. And just to let you know, the focus will be into the future as opposed to what's been done in the past. And there will also be a focus on some work that I'm doing with students and others at Case Western to look at some new ideas for what can be done for SETI. But I thought I'd start today by doing a quick overview of a few of the points that we made for those of you who were here a week ago, and then for those of you who weren't, then we can sort of see some of the bottom lines that we came up with from last time. So we did spend a little time last week looking at this question of what the odds are that there are extraterrestrial civilizations that we could in principle detect or be in contact with. The context for that discussion was this simple but interesting equation by Frank Drake, the Drake equation. And we spent some time looking particularly for the terms on the left-hand side of this equation corresponding to the rate of star formation, the fraction of stars that have planets, and the number of planets that are Earth-like, where Earth-like is defined as at least potentially habitable for life in terms of temperature and size and so on. And the conclusion that we came to last time is that now more than ever, based on discoveries by astronomers, we have a handle on the value of these three terms, and they're increasingly well understood, especially in the context of the detection of exoplanets. We talked about the results of NASA's Kepler telescope satellite, which operating over 10-year time has detected well over 2,000 exoplanets, and has demonstrated statistically that virtually all stars, at least stars in our nearby solar neighborhood, have planets. So something we didn't know even 15 or 20 years ago. We had no idea what fraction of stars had planets, and the answer is the vast majority of them do. At this point, there's quite a good handful, 21 to 55, depending on how you optimistically count, of potentially habitable exoplanets that have been detected by Kepler and other techniques for detecting these exoplanets. Of course, we don't know if there's life on any of them. We don't know, none of them have been detected directly in terms of making observations, but their existence has been inferred by the occultation techniques we discussed last week. And when you take the statistics of this, the observations of Kepler and what will soon be the TESS experiment continuing to search for exoplanets, the expectation is that exoplanets are ubiquitous, that there are expected to be hundreds of plausibly habitable worlds within our near solar neighborhood, and then billions of habitable worlds in our galaxy, perhaps tens of thousands capable of, or more capable of supporting life. So in terms of planets, we have a great idea that there are many planets in our galaxy. We also talked about the next term, which is a fraction of those planets that have those Earth-like planets where life will arise. And again, that's much less certain and requires a more direct detection of information from these planets. We talked about the example of the James Webb Telescope as one of the first efforts to try to look for atmospheric data that will be launched in 2021. And then finally, we talked about the last three terms corresponding to the fraction of those planets where life develops into intelligence, the fraction of life where that intelligence develops a technical civilization, and the average lifetime of that civilization relative to the star formation rate. And all of these terms, as we discussed last time, are wildly speculative. We have no idea how to estimate those numbers in the context of any other example besides our own, and we don't know whether we are unique or typical. We also spent a little time in the last talk talking about Enrico Fermi and Fermi's paradox, this idea that if technical civilization did exist at any time in the 12 billion year history of our galaxy, that it would, if it had the propensity to spread in a geometric pattern, the way that life often does, that there would be an expectation that the entire galaxy would be filled with that technological life, either in the forms of robotic probes or whatever your favorite mechanism from jumping to star, and it would take on the order of handful of million years, 4 million years or so, to completely fill the galaxy. And the question that Fermi asked is, if it takes such a short time to fill the galaxy relative to the 12 billion year age of the galaxy, then where are they? Why don't we see them all over the place? And we talked about a variety of different consequences of the non-detection of technological life in our galaxy, searches for evidence of highly advanced civilizations. So this is an artist's rendition of a so-called Dyson sphere or megastructure surrounding a star. And again, astronomers are getting better and better at looking for unusual signals from stars that would have evidence for some technological advanced civilization. But so far, no evidence has been detected. Although increasingly, as satellites and telescopes get more and more sensitive and sophisticated, the number of unusual things begins to increase. One example we looked at last time was Tabby's star, which has unusual light variations, but again, eventually astronomers concluding that these were consistent with an irregular collection of dust in the vicinity of the star, not aliens. So we ended up last time with the answer to the question of what are the odds, with the conclusion that even though there are many stars and many planets in those stars, the probability of life forming and that the life then would evolve into technological civilization where we could communicate was very speculative. And so we cannot, at this time at least, calculate the odds. We don't know whether technical life is common or extraordinarily rare. But one thing that's worth remembering at this point is that we've barely looked beyond our nearest neighbors. If you ask what are the collection of stars that we see in the night sky visible to the eye, or even the collection of stars that have been explored by techniques of the search for extraterrestrial intelligence, the answer is it's a tiny, tiny fraction of the stars in the galaxy that we've been able to look at. So the effort to search and to look and explore has really only just begun. So I want to, before I dive into the question of, well, how shall we search for direct communication from those hypothetical technological civilizations, I want to go through an exercise of what I would call kind of a toy representation of what you would call the scientific method. This is the kind of presentation you'd see about the scientific method that you might have gotten in your middle school or high school classes, and it's not exactly how things really work on a detailed way, but it gives an overview of basically what the approach is, how we basically go about things. So there's a set of steps to basically move science forward. Based on some collection of information and knowledge or observations that you already have, you develop or you refine a theory, or you make a particular hypothesis about the nature of the universe. In other words, you come up with an idea that might or might not be true, and then you infer a consequence of that hypothesis or theory that at least in principle should be measurable. Then you design an experiment to measure that particular thing. And then once you have that measurement, you take data with that experiment that would at least in principle support or possibly refute the theory or hypothesis that you started with. And in the case, in either case then, you confirm your results with repeated experiments and improved accuracy and precision. So the idea is that you can have a brilliant and beautiful idea, but the question is it really true? And the answer is you have to figure out what the consequences of that idea are, and then go and actually make measurements, collect data to either verify or support it, or if it doesn't match, the data doesn't match the theory or the hypothesis, you have to then say, well, if there's something wrong with that hypothesis or theory, we have to start again. So as one example of kind of this process at work, you could consider the application of the discovery, the idea of the Standard Model to the discovery of the Higgs boson at the Large Hadron Collider. Now, I'm not going to talk at all about what the Standard Model really is or how this measurement was made. And the picture I have here is just schematic in the context of how this works. But in the latter part of the 20th century and into the 21st century, physicists studying the fundamental nature of matter began to develop had developed a fairly sophisticated sequence of ideas about how fundamental matter is put together. And as far as we understood, direct evidence supported the idea that matter was made out of some combination of particles that we would call quarks, which would be, for example, the particles that are found in the center of a nucleus are made of quarks. Leptons, which is another category of fundamental particles that would include, say, the electron that you'd find in atoms. And that these interactions then were governed by a set of rules, fairly sophisticated and mathematically precise equations and methods that are then applied in the context of interactions that can be categorized in the terms of four fundamental forces. And this is a picture that was basically put forth in the 20th century and then developed with increasing refinement with a series of measurements over the course of the period of time since the idea was put forth. Refinements both in the theory and in the measurements itself. And as those refinements came along, it became increasingly the case that Standard Model was basically presented in a certain form where it could make, where the consequences of that model predicted that a particular additional particle should exist, a boson that was predicted by Higgs and other theorists. And so in the era of the Large Hadron Collider, experimentalists built an experiment. It took many years and billions of dollars to build, but it was built, and the measurement was made, and lo and behold, the boson was detected as predicted. So again, you have a framework, a precise and a mathematical framework for describing how you proceed in doing science in this context. So here's the problem. The problem is that for SETI, the hypothesis that there exists extraterrestrial civilizations does not, in and of itself, lead to any specific particular consequences that we can measure. In other words, I'll put it this way, there's no standard model for ET. We can't write down an equation that allows us to translate our expectation about how such a civilization would and could try to communicate to us in any kind of sort of rigorous and standard way. It's a serious problem, and it has to be acknowledged. I mean, if you ask the question, how does SETI sort of hold itself up against other forms of research in physics and astrophysics, the answer is in part, well, it's an enterprise, it's an exploration, but it's hard to know what you're going to do, and it's hard to say exactly how you best ought to proceed because there's no consensus, at least not in terms of fundamental observations, about what you would expect. Now, it is true that the search could arguably be well motivated in the context of people who are doing observational astronomy and astrophysics. In other words, people who already have training to look up and see and observe and measure. This would be the category of people who might be best suited to best qualified to carry out this kind of research. So we can give it a try, but anything we assume about ET, how can I put it? Anything you assume about ET is likely to be wrong because we've never detected anything at all about them. We don't know anything about their civilization. There's no equation, as you will, for little green men. And anything we're likely to guess is wrong. So what do we do? So the approach, and it was developed by Philip Morrison and other physicists in the middle of the 21st century, is that for the search for extraterrestrial intelligence, you make instead of a hypothesis, you make what I would call an ansatz, essentially a method to proceed in the lack of knowledge, right? You basically say, let's suppose that the following is true. And I call it the anthropomorphic ansatz, where the word anthropomorphic means we're basing it on ourselves in some sense of the word. So the two assumptions that SETI itself is based fundamentally on is first, well, the first assumption is sort of a double assumption, that they're out there, that's a big assumption, and that they're trying to talk to us. If the alien civilizations are determined to stay hidden from 21st century human beings and an advanced civilization, they will succeed. But if at least some fraction of them or some part of them is trying to communicate some information to us, perhaps that's worth keeping in mind. And then the second thing you could say is, well, we don't have any idea what kind of technology the aliens are using, but they're likely to be more advanced than current 20th century Earth, very likely. And so they have if you will, a repertoire, a range of possible technologies that they can use. We have no ability to apply a search for a technology that we have not yet discovered or understood or developed. But we can use our own current technology. So in other words, you changed the question from how should we detect the aliens to how would we detect ourselves if we were trying to communicate with ourselves from some other star in our galaxy. And then see where you go with that.
As you show these exoplanets, do you just assume they're spherical? And what's your theory about why our planets are spherical?
So you can demonstrate with absolute confidence that any structure that has a mass over a certain amount that's made of what we call ordinary atomic and molecular matter, in other words, the elements that we expect, will condense into a spherical shape. And that size is, roughly speaking, easily the size of the planet Mercury or bigger. In other words, it's hard to make a structure that's larger than that isn't spherical unless you in terms of natural processes of coalescing. So when we detect exoplanets, the primary mechanism for detecting exoplanets is the measurement of starlight coming from a nearby star and then watching the intensity of that starlight dip as that planet goes across. And again, you infer that the planet is approximately spherical, and then you notice how much of the starlight is removed from the signal, and based on your theoretical understandings of approximately how large a star of a given intensity and a given brightness and a different color, specific color ought to be, you can then infer the approximate size of the planet. Yes, that's the technique. But yes, absolutely, they assume a spherical planet, and they assume that the planets themselves are made out of ordinary matter, everything from rocks, iron, gas, whatever you find in our own solar system. Yeah, that's the assumption. I mean, I will point out that the problem with the ansatz is, how can I put it? It's chauvinistic, yes? You say any speculation you have about the nature of the aliens, maybe the aliens are, giant slugs made out of, instead of carbon-based life form, they're silicon life-based form. You could make that assumption, and it's almost certainly wrong. Or you can make the assumption that they're sort of like us and they have the same kind of technology that we do. And that's almost certainly wrong, too. But that's the only assumption you can make and then proceed, because any other assumption you make, you either quit and go home, or you say, I don't have the technology to do it, so I'm going to continue forward.
Thank you for joining us. You've been watching Corbin Covault, discussing the probability of intelligent life on planets around stars other than our sun, and the question of why, if it's out there, we haven't met it yet. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Professor Covault will discuss current searches for extraterrestrial intelligence, aka SETI. Now, back to the talk.
Current Earth communication technology was what motivated the original SETI efforts, which started in the 50s and 60s. And if you had asked in the 50s and 60s, how shall Earth-based creatures communicate with other Earth-based creatures who happen to be in space, the answer is you use radio waves, right? I mean, the moon landings were broadcast from the moon to Earth on a radio wave. And we know, and we have known for a long time, how to send, transmit, and receive radio signals across interstellar space. So the first initial SETI efforts were based on the assumption that this is the best way we know. It's the current technology that we know. And this is an example of an array of radio telescopes. Again, there was a famous paper that was written in 1959 by Goccioni and Morrison that basically laid out this ansatz, this idea for proceeding with measurements, assuming that they would be using Earth-like technology to transmit a signal. And this whole approach for radio SETI, the search for a radio signal that could be beamed to the Earth, continues today. This is a picture of Jill Tarter, who heads the SETI Institute, and she's standing in front of the Allen Telescope Array, which is an array of sensitive radio detectors that operate over a range of different frequencies, and they scan the skies. They're located at a beautiful place in northern California, and for years now they've been scanning the sky, looking at different frequencies at different locations for evidence of a signal that would indicate a communication by an extraterrestrial. Now, of course, to date, so far they haven't seen anything, but this effort continues. I mean, it is the technology of the 20th century, but they've only barely scratched the surface in terms of the frequencies that they've looked at, the sensitivity that they've looked at in terms of the observation time at any given interval, and the depth into the corresponding depth into the galaxy that would correspond to it. In other words, we have not scanned the galaxy in the radio SETI. It's still a process that's going on, and it's a process that I expect will go on for decades because there's still more to explore. But if you ask the question, what is the fundamental communication technology of the 21st century? The answer is not radio waves. Okay, so radio waves, the last mile to your cell phone. But if you ask, if you sit down at the internet and you basically log into a site in California or someplace else, all of that data is primarily transmitted through fiber optic cable, which uses a range of frequencies corresponding to the near infrared upward into the optical frequencies. In other words, short wavelength optical signal is the way that the 21st century communicates. The signal is intrinsically digital as opposed to a manifestly analog signal that you get from radio. You can create the signal in a clean and sharp and high sensitivity, high signal strength method by using laser technology. And you can make the signals very short, which gives you a high flashes of on and off that indicate binary data on time scales of a few nanoseconds or so, which gives you a much more rapid way of sending information much more efficiently. And that's what we've moved to in the 21st century. And just like we use optical technology for communication on the surface of the Earth through fiber optic cable, of course optical photons have no trouble going through outer space once they get up there. And indeed, NASA is now moving to a communication platform for interplanetary and interlunar communications that would be based, instead of on radio frequencies, it would be based on near-infrared and optical frequencies. So in order to do that, of course, you need a way of sending a laser beam back and forth between the Earth and the Moon. So this picture basically shows you a kind of a schematic idea. There's on the Earth somewhere is basically a little multi-pronged laser turret, if you will, that's beaming a signal through space to a satellite that's in orbit around the Moon. This was NASA's Lunar Laser Communication Demonstration, which happened in 2013. And again, another signal then comes back. It's picked up by the telescopes in the same turret, and it successfully demonstrated a laser communication system in space. This system was approximately 400 times the data rate transfer that you would get from a normal radio signal. They sent a YouTube video back and forth between the two locations. It works very well. So suppose that we move to the 21st century and we say, what are the instead of using radios, maybe they're going to use a slightly more advanced technology. What would we assume? What if we say an optical search for extraterrestrial intelligence? What should we assume? So it's a few steps that basically boil down to these assumptions. So the first step is that we assume that these alien civilizations can build powerful pulsed laser systems, megajoules or higher. Now, of course, we don't have those lasers, at least as far as we know. We're not putting those lasers in outer space to communicate with anybody outside, but it's at least within a realm of technology that you could put such a laser on some kind of orbitable space platform. And then you could point that laser, the aliens then, they have that platform out in space. Maybe it's in orbit around a planet. Maybe it's in interstellar space somewhere. We don't know where it is, but it's somewhere within, say, tens or maybe 100 light years or so of Earth. And it has a mission to basically send laser light pulses to any planetary system that's within its range that might have but might be inhabited by technological civilizations. And so the laser in space swivels and points in the direction of our solar system. The sun is out there, and it fires. Choo choo choo. Well, okay. So in space, there's no noise. There's no choo choo, but it fires some collection of pulses. And of course, for maximum efficiency, those pulses want to be as short as possible. A nanosecond, that's a billionth of a second, or on the order of a few of those. And those pulses are then directed. They travel across the light years to our solar system. Of course, the laser beam is very narrow and very efficiently beamed, but of course, over that vast distance, the beam spreads quite a bit. By the time you get a laser beam that's coming from, say, a few light years, the beam itself will be several tens of astronomical units by the time it gets to the solar system. So it's basically a giant wave of light, very thin, very dispersed wave of laser light that then sweeps into our solar system. So there I've kind of indicated that it's kind of a purple line coming in, and then that beam then encounters the planet Earth. And if it just so happens that on the Earth you have some telescopes that can detect in a very narrow pulse of light, then you can look for and detect that signal sent by that alien. So this idea is not brand new. It's relatively modern, but we're not. There are several people who have tried to invest some time and energy in doing that. Probably to date, the strongest effort has, at least an original first generation effort, was by a group led by Professor Paul Horowitz at Harvard. They basically built a relatively small telescope, 1.5 meter primary mirror, to do a scan of the sky. Using a set of position-sensitive photon detectors that could see rapid flashes of light. They split the signal optics, and they used some fairly sophisticated electronics to basically look for that pulse. The system was built by a team of graduate students and postdocs, and it seemed to work pretty well, but they kept finding that when they basically pointed this telescope at the night sky, that over the course of the night it's not that they didn't see anything, they'd see lots of things. And they looked like there were pulses coming from all over the sky at different times, kind of spurious background events. They ultimately concluded that most of these spurious events were due to fluctuations in the night sky background or to cosmic rays interacting with the Earth's atmosphere. And they were going to try to improve that and so forth. If you look at the website, still there. They say in 2013 they're planning to get it going again, but it still hasn't come up. Hasn't been operating, at least as far as I can tell, since about 2010. But it's not a new idea, and people have started, people had invested some time and energy into trying to build a detector for this. More recently, the little bit of money from the Hawking-Milner $100 million breakthrough Listen for SETI, which is a project that's funding a number of different things, including optical, radio, SETI, and other projects, is invested some time and energy into a new optical SETI group that's operating at the Lick Observatory. And the thing that this approach uses is actually takes spectrum from the sky, and since it's a laser, it will be a very narrow spectrum, be a very unique spectrum, and they're looking for the evidence of this in an observing program that will look at least the nearest 1,000 stars. And that program is already underway, but it requires a telescope to use, and of course other people use the telescopes as well. So they have to share the telescope with whatever else they're doing. So all of this is basically this ideas of optical SETI were in the air over the course of the past decade or more, approximately, as the new way to go from radio SETI. And as a physicist, experimental high-energy astrophysicist, I was not, my personal self, I was not, I mean, I think SETI is very interesting, but I wasn't working on it at all. And this would be in the period of the mid to late 90s and early 2000s. My personal research background is I'm a cosmic ray physicist. The thing I do is I try to understand high-energy gamma rays and cosmic ray particles coming from energetic sources in the universe, astrophysical sources such as neutron stars, supernovas, active galaxies, and so forth. And one of the approaches that's very common in the field is to look for, is to build experiments that are sensitive to flashes of light in the sky, because when a high-energy gamma ray or cosmic ray hits the top of the atmosphere, it will generate a flash of light in the sky. That high energy then gets dissipated in the atmosphere. You end up with a little flash of light that's very analogous to the glow that you see from radioactivity. And that flash lasts a few nanoseconds. And if you build a detector to collect that light and detect it, you can basically measure the arrival of cosmic rays and gamma rays. So a group of us had built an experiment to do this called Stacey, which operated in the 2000s. And it was an experiment that was located at Sandia National Thermal Test Facility. This is a facility at Sandia Labs near Albuquerque, New Mexico. This facility is basically a giant solar power test facility. It has a 10-story tower and a whole bunch of heliostat mirrors that can be used to focus light from the sun onto solar collectors and thermal furnaces at the top of the tower. And they don't use this during the day for solar energy because the sun's not out. So we came in and said, can we use your experiment at night to do cosmic ray astronomy and gamma ray astronomy? Oh, and by the way, we had this idea, well, what about those little flashes of light from optical SETI? So we actually, well, again, our experiment was funded by the National Science Foundation. We didn't really tell them we were going to do this, but we took a little bit of data over a course of about a year or two and squeezed it in here and there, and we observed 187 stars with this experiment, and we presented non-detection of the search for laser pulses, just as the kind of described. And when the experiment was published, it was the most sensitive experiment, the result of its kind. This is a paper in the journal Astrobiology. Furthermore, the technique was particularly effective because there was zero background. So that's the story where we're at this point. And what I'm going to finish with is a new idea for building an observatory that's dedicated to optical SETI as opposed to something that's piggybacking, so to speak, on other projects.
You have all these arrays that are out looking for a signal.
Yes.
And my question is, if you receive a signal, how do you know it?
How do you know that you've got something that's real, that is, and particularly if you see something, how do you distinguish something that would be a clear indication of a technological civilization trying to communicate with us versus a signal that is an unusual and interesting, but nonetheless natural astrophysical phenomenon that you hadn't heretofore discovered? That's the way I like to put it. And the answer to that it's not easy to answer that question. When you're doing radio SETI, you're always picking up some signal strength, and that signal strength modulates in certain ways. So radio astronomers basically have certain criterion for looking for what you would call artificial indications in the fluctuations of their radio signal. Say somebody sent you say you heard in the signal fluctuations that were very unnatural and irregular, or had a mathematical pattern to it, like the prime numbers or something. These are the kinds of things people talk about for radio signal. For optical SETI, one of the great things about optical SETI is if you design the experiment correctly, it looks like there's no natural astrophysical or terrestrial phenomenon that can mimic the signal. Now, I've showed you the results from from Harvard, where they had problem with false positives. But you can see from the Stacey experiment, we got the number of false positives down to precisely 0. And I'll explain how we do that in the next section when I talk about the next thing we're going to do. My idea is this: if you can build a SETI detector where you never see anything natural, you're guaranteed that the natural detection rate is so low that if you see something, it'll be interesting. That's where you want to be, because then you don't have to argue, is it real or is it natural? You can certainly say, whatever it is, it's very interesting and we need to look at it more deeply.
How long would it take for a signal to reach us from one of those planets that might be habitable?
The kind of picture I'm painting here is a signal that's transmitted from our relatively close to us in our current astrophysical neighborhood. So that would be a signal that's, say, within 10 to 50 light years from us. So that signal would have been sent to us. If it's arriving today, it would have been sent at least 10, possibly 50 years ago from a relatively close distance. And it's worth pointing out that both for radio and for optical SETI, the reach into the galaxy in terms of the sensitivity for these kinds of signals is relatively close. I mean, our galaxy is much bigger than 50 light years across. So for now, we're looking in the sort of just down the street, not way out of town. No.
I think you've more or less answered it, because I was interested in what the criteria were for determining noise from a real signal.
That's a great question, and it causes. How can I put it? I went to a SETI conference when all of this was going on, and SETI conferences are very interesting, very, very fascinating people, and they had a panel on this question: how shall we agree that this is from ET as opposed to a natural phenomenon? And several of the panelists stood up and said, what we should do is we should make a protocol. We should come up with a rigid set of what the signal needs to do to pass. And it has to go through all these checks, and it has to and everybody has to agree that it does this. So that was the view of one panelist. And then it got to Paul Horowitz, this fellow who I'm talking about, who built this other experiment, and he said, I'm not gonna agree to that. If I see something interesting, I'm gonna publish it right away. Right? So this is how science, how can I put it? Science isn't done by committee, right? People will, at the cutting edge of science, the first results that come out can be interesting and controversial, but not necessarily conclusive. But I guarantee you, if one experiment sees a signal, say an optical signal, with a relatively small telescope like the kind that Paul Horowitz put forth, then as soon as that result goes out there, all the big telescopes on the planet can start pointing in that same direction, seeing if it repeats, making more sensitive measurements. So again, how science works is, even if you have an initial result where it's hard to tell, is this real or is it not? If it is real, the more you look at it, the more you'll be able to say, oh, this is the properties of it. You have more precision, more accuracy, more confidence in what you're seeing. Yeah, it's the signals that come and then go away forever. Then you don't know what to do with it. Then those aren't convincing. You need something that has staying power.
We hope you've been enjoying the Origin Science Scholars Program with Corbin Covault. Professor Covault is professor and co-chair of physics at Case Western Reserve University and a fellow of the Institute for the Science of Origins. In the second part of our talk, we discussed existing programs to search for extraterrestrial intelligence. In our final segment, Professor Covault will discuss his own plans to construct a specialized telescope to look for intelligent life that is trying to communicate with us. Now, back to our talk.
This is the last part where I'm going to talk a little bit about our ideas for putting together a detector for optical SETI, and it's a relatively modest proposal in the context of how to build an observatory that's dedicated to looking for the flashes of light that ET may be sending us. And the key assumptions we're making is that because the low duty cycle and the aliens are going to use lasers that are pulsed at a very short time period, a few seconds or so, a few nanoseconds or so. In other words, times that are very short compared to natural fluctuations that you expect to see in the sky. Lightning bolts, airplanes, twinkling stars, all of these fluctuations are hundreds or thousands of times longer than the the very short pulses that you'd get from a laser. And as far as we know, there's no astrophysical phenomenon that can make such a pulse. And then the second assumption that we're going to make is, well, it's nice to have a very fancy telescope that can take a really clear picture. But all we really want to do is collect as many photons as we can, as much light as possible in a bucket from that wave as it goes through. The more light we get, the more signal we can see. It's not that important to figure out exactly where the light comes from. The first thing that's important is to actually detect it, and detect that flash of light confidently in excess of the background of skylight that's always there. The night sky, as you know, is not perfectly dark, and anytime you look at the sky, there's light coming down from all directions, not to mention starlight and all the other things you can see. And you want to distinguish your pulse signal relative to that. So we need a light bucket, and our idea for a light bucket is this thing called a Fresnel lens, a plastic transparent lens that has etched lines in a particular pattern of circles around that allow the light to be focused and can be built relatively large and relatively inexpensive. This is a picture of a Fresnel lens, 3 by 3 meters, so that's about 10 feet square, that was built by a company in Japan. They build the world's largest Fresnel lenses that's used for solar power applications. And so you can collect light on the order of 3 meters across without building a giant telescope or made out of metal or glass, where the costs could be tens or hundreds of times as much for such a large system. There's this one company in Japan that builds these, and we've talked to them. In fact, we talked to them and we said, well, okay, we're not ready to buy one of your big lenses, but just send us a small one, maybe about 1 meter by 1.2 meters, about the size of a small table. And here you can see we've set up the lens on a little stand, and we've put it on top of the A.W. Smith building in Case Western, overlooking the Case Quad. And we used it to basically make images of flashing airplane lights that were on top of buildings or in the sky. And you can see we made measurements of the optical properties of this lens. The lens is not the best lens. If you find them on the back of vans. Sometimes you have little magnifying Fresnel lenses for looking at books and stuff. They're common, they're inexpensive, but they're not very good optics. But we don't really need a clear picture. We just need to detect the signal. So our design concept at Case Western is that we want as large an area as possible, because the more area you have, the more sensitive you'll be to the signal relative to the background. You want a detector that will respond quickly, which is to say to a signal that lasts only a few billionths of a second. The standard classical way to detect this is to use photodetectors known as Photomultiplier Tubes, PMTs for short. And it turns out, in my laboratory, I've got boxes and boxes of old PMTs from old experiments that are just lying there waiting to be used. They were kind of donated to me and said, can you do anything with them? And I'm thinking, you want to look at as much of the sky as possible, because any assumption you might make about where that stellar platform, where that laser platform is, or how close it is, or where it's located, that's just another assumption that you might be wrong about. And the nice thing about this is if you look at the large swath of the sky, you don't need accurate pointing associated with an expensive telescope. And then this is the key idea. Instead of building one telescope where you could have a false positive, you build multiple telescopes so that you insist that each telescope sees the same signal at the same time, to within a few nanoseconds, right? So if you get, and again, since the pulses only last a few billionth of a nanosecond, the odds that they would accidentally go off at the same time go down exponentially or faster when you insist on this so-called simultaneity or coincidence condition. And this is the key concept to our design. And because we use a coincidence to reduce the background fluctuations, we can get away with using relatively inexpensive technical mechanism for collecting the light. So this is a schematic of how we might build this one of these telescope modules. It's basically a little hut, twice as high as a typical person, and the hut has a removable roof, and then it has a false ceiling made out of one of these large Fresnel lenses. And the Fresnel lens focuses the sky onto a camera that's made out of these photomultiplier tubes. In the ideal case, you can tip the lens so that you can look at different parts of the sky in elevation, but you mostly just open up the roof and let the light from the sky come in, and as the stars move across the sky, moving from east to west over the course of the night, you collect data, you scan the skies in your camera. And that's kind of the basic idea. Well, we have a name for it, the Scanning Observatory for Optical SETI, which we call SOPHOS. And this would be one of one telescope. But then, again, one telescope, you have a false positive, there's some fluctuation, somebody, I don't know, a firefly dies in your detector, anything could happen. Radio interference, who knows, all kinds of things could happen. So you say, well, I want to be sure I saw something. So then instead of one telescope, you have two. And the key concept is that you have electronics between the two that basically says at the same place in the sky, at the same time, to within a handful of nanoseconds, both see the same flash of light. Now again, I'm not taking a spectrum, I'm not doing anything sophisticated, I'm not taking a very careful image. I'm just saying there's a flash of light in the sky from the same place in the sky within a few nanoseconds. And that reduces the probability of an accidental background rate many, many orders of magnitude. And then those events where they have a same flash at the same time, you store in the local data. You basically put an accurate timestamp on them. GPS will give you the timestamp to within a few nanoseconds, and you store the data. So that's one approach. And then, but wait. Now you got two together, and they both have to be the same. What if there's a flash of light that they both see, but it's not really from ET? Maybe it's from a cosmic ray or some other phenomenon, like the kind of thing that we were looking at for gamma rays and so forth. So instead, the next thing you do, instead of two, you go to four. In other words, you have two pairs, each of which operate in coincidence, and all four of them have to see the same flash at the same time. And you separate the two pairs by a large distance so that a cosmic ray that comes into one will not be seen by the other one. So you're absolutely convinced that anything you see is corresponding to a flash of light that's coming from this large plane of laser light that's hitting the entire planet, and ought to have the same shape, the same intensity, the same signal in all four telescopes at the same place in the sky to within a few nanoseconds. All of those probabilities make it almost impossible that there'll be a fluctuation that will happen at the same place at the same sky, at the same place at the same sky, that will cause you to say, oh, I saw something. And when you actually put this design together, you can predict, based on natural phenomena of cosmic rays, that the accidental rate, the rate of false positives, will be approximately less than 1/10 of an event per observation night. In other words, 1 in every 10 nights, in the middle of the night, you'll get a bing and nothing else. And that's your background. That's your ignorable signal. And anything that comes in more rapidly than that, say you're observing in the middle of the night and you get bing, 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 right? Something that comes in real quick, or bing, 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 something regular, or any other thing that isn't zero is interesting. That's our approach. Okay? Oh, and so where should we put it? So this is being developed at Case Western, and most of you may know Case Western has a research farm located in Hunting Valley, the Square Valley View Farm. It turns out that there's two very nice locations at opposite ends of the farms. We've already talked to the people who run the facility. They've given us permission. We've taken some background light data at these locations. You can actually deploy this. Now, let me tell you, northeastern Ohio is not optimal for optical astronomy, okay? But at least this is a reasonably convenient place to basically test our experiment, make sure it all works, and then maybe consider deploying it for good at some location in the southwest where you get clear skies most of the time. We wouldn't spend a lot of money on building, on the buildings themselves. I mean, for our prototypes, as you'll see, we're literally throwing up plywood. But it turns out you can build relatively cheap huts. The design for this is made by a company called Skyshed. And the trick is you put a garage door opener on the roof instead of the side, and you can pull the roof off. And amateur astronomers build these things all the time. All you have to do then is basically put the Fresnel lens in the location where the ceiling would be, and you're all set. These can be assembled from parts from Home Depot with a crew of volunteer undergraduates relatively cheaply. So how much would this thing cost? So this is my, and now how much would you pay? All right, so the most expensive component are these Fresnel lenses made by this special company in Japan. We have the photodetectors, and then you can see there's on the order of tens to handful of $1,000s for all of the other components. If you throw it all together, you give me $200,000, I will build you 4 telescopes that will be the most sensitive experiment for optical SETI in the optical range with these flashes at these time scales. And by the way, this number, of course, there's always a disclaimer. This number excludes labor. Like, in other words, everybody who's working on it is working on it for free. Not inconceivable. Computing, and then digitizers. If you really want to prove that the signal is really, really real, you'd like to take a snapshot, digitize each signal, and make sure they look exactly the same from camera to camera. The digitizers, annoyingly, roughly double the price. So I don't have $200,000 in my pocket. Can you build this experiment piecewise? Can you put together prototypes? So again, the full system, depending on how many of the bells and whistles, where you're going to deploy it, maybe 200,000 if you put the full working digitized system into southwestern U.S. with all the requirements there, maybe $500,000 altogether. That's really cheap for an observatory. Just saying. What about for a tiny fraction of that, say $60,000? Well, for $60,000, you could build 2 of these modules. You'd skip the tilting and stuff, but then you'd at least be able to look for the coincidences, and you'd have some sensitivity to the brightest flashes from a laser. Not as much as you would get for the 4 together, but nonetheless. For half that money, of course, you can build 1 of these. With only 1, you can't do the coincidence, so you have no sensitivity to the optical SETI signal, but you can at least measure the optical performance of the system. And then if you're really broke, like we are, you can build a half size out of these smaller lenses, roughly scale the rates, and at least test things and make sure things are working. So in fact, we don't really have $10,000, but nonetheless, we're charging ahead. So this is an undergraduate student, Anika Gabrielle, a physics major. This is work that she was doing in our laboratory to put a box together with a Fresnel lens so that we could, it's hard to imagine a more primitive looking telescope, but nonetheless, you've got a box, you've got a Fresnel lens, and you've got a camera that you can basically put in. This was done in 2 summers ago. Last summer, I had a master's student, Jacob Brookman, who's really come into his own in terms of the work that he's doing. And he worked in particular on these photodetectors, these old ones, getting bases replaced with new bases, calibrating them as best as possible, and then making sure that our old electronics could be tuned up and processed so that we could do essentially a simple coincidence test with 4 multipliers working in 1 camera. It's, again, not going to be sensitive to SETI, but you can at least look at the background rates and make sure that things go. And at this point, we're literally waiting for clear nights where we can actually go up on the roof of the building in A.W. Smith and at least make sure that the whole setup works. We've already tested it in the lab in a dark box. That's what you're seeing on the right-hand side there. And everything's, we basically put a fake SETI signal in by a flash of blue laser LED, and everything seems to be working just great. So where can you get the money from this? Can you get it from federal funds such as the National Science Foundation or NASA? The answer is probably not. These places are more than happy to invest money in the search for life in exoplanets, but they don't tend to wade into the issue of SETI. There are foundations such as the Templeton Foundation that have grant programs. We have applied in the past. We will try again, but nothing new. Keck is another example of that. There are other foundations that are specifically dedicated to astrophysics and the search for extraterrestrial intelligence. The SETI Institute is one example of those. And of course, there are funds from the Breakthrough Listen initiative. I have had several conversations with Jill Tarter by email. She is interested in our project, but there's no funds available yet. You can also ask individual donors for money. It's not that much to get this thing going, but of course everybody else has their hands out. And one kind of crazy idea is you could, go to crowdsourcing. And now Kickstarter and GoFundMe don't really work that well, because for those things, we're basically promising to deliver a product. Like, here's the latest, can opener or whatever it is. Give us some money and we'll give you the prototype. We don't have anything to give. We're building something that we're going to keep. But there is a crowdsourcing site called Patreon, which mostly supports artists. Just this morning, reactivated. This site was on for a little while, but we had some difficulty keeping it up, but it's on and going now. And we do have something, patreon.com/SETI. So I now have a new crowdsourcing initiative. And here's the point, since it's so inexpensive, even a few dollars can make a difference. If you go to this site, you can donate, you can buy a subscription to our SETI detector for as little as $1 a month. If you do that, you get your name on the prototype and thanks and so forth, and you get access to the data, all kinds of things. So you're more than welcome to join us as we put this together. And all the money that's donated, none of it goes to anybody's salary. It all goes only to building the experiment. So I'm almost done here. 2 more slides. So what's next for our project? Well, we do need to. We do have an undergraduate who's looking at electronic simulations to verify our predicted sensitivity. We do, in order to actually do this coincidence measurements, even with a tiny prototype, we need more Fresnel lenses. These cost about $1,500 each, so we're almost got enough money to basically purchase another 2 or 3 of these from our vendor in Japan. We do need to finish the testbed triggered timing, all the electronics associated with the signal processing and the photomultiplier tube cameras. These are mostly done by the student Jacob Fruckman, and we're in pretty good shape for that. And of course, we have to come up with what I would call a somewhat stable funding plan for putting this together. We do get lots of volunteers, everybody from high school students to Case Western undergraduates to random people come to me and say, can I help work on that? And I've no problem, that's great, but we got to get the thing built before we can start taking data. But nonetheless, we're often going, and our hope is that we'll be in a position to prove the principle of the experiment sometime by the summer of 2020, and then at least if we have a clear path for funding, construct the world's most sensitive observatory for optical SETI on a time scale of about 2 years. Again, this is a project in fits and starts over the course of the past few years that I think we're finally get going on. So one last reflection, and this is about the larger issue as opposed to my specific thing. Going back to this ansatz that we must look for the signal that corresponds to our own technology. Are we looking for keys near the lamppost, right? It's the old story. I drop my keys, the policeman comes along, the guy's looking under the lamppost. What are you doing? He says, I'm looking for my car keys. And he said, oh, you just dropped them here? He says, no, I dropped them about 3 blocks back, but the light's here, good, so I can see it. Obviously, the keys aren't there. I mean, are we doing the same thing? If we're looking in the optical wavelength for pulses of laser, maybe this technology is horrendously primitive compared to what's actually being used to communicate in intergalactic civilizations. But it's the only place we can look because it's the only technology we have. So we really are looking for our keys near the lamppost. But nonetheless, there are so many planets. That's really exciting. And it's relatively easy and inexpensive. We're talking, in terms of human effort, endeavor, and costs, this is not a moonshot. We're talking handfuls of people, tens or hundreds or maybe millions of dollars, depending on what your favorite approach is. Not that expensive, not that costly. If we did find something, the result would be extremely exciting. I think that would be the understatement of the day. And then, wouldn't it be awful if there was a signal out there that was easy to see and we just hadn't looked for it? That would be almost embarrassingly bad, especially if we had the technology and we simply didn't have the will. And therefore, even though we don't know the odds, even though we can't predict this probability of success, let's look. Let's look. Thank you very much.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.